So welcome to the tutorial on the serum anion gap. This is going to be a two-part tutorial, one on the serum anion gap and one on the urine anion gap. And what I hope to accomplish in these two tutorials is give you a better understanding of how this formula is calculated and a more easier way of remembering the formula so that when you're on an exam or on the floors you can calculate these values quickly and accurately and hopefully accurately interpret the results. So in order to understand the serum anion gap or any anion gap, you need to know the law of conservation of charge, and that's actually how the gaps came into, I guess, existence. Because the law of conservation of charge says that all the positive and negative ions have to equal each other. So the sum of the cations must equal the sum of the anions. And that's also true in the bloodstream. So when we look at the serum, we have a number of cations and anions, some of which we measure and some of which we don't commonly measure. When we add all of those together, we have to have equality. And let's look at these cations first. The most common ones, of course, are sodium, and we've got potassium as well. Now we have some other cations that we could measure, but historically we don't because we didn't have easy ways of measuring these cations. I'll show you what those are in a moment. Let's see if I can change the color. Those are calcium, and we've also got magnesium. Now these are easily measurable in today's day and age, but they weren't measurable back in the day when the serum anion gap was being developed, and so we don't commonly include them in our anion gap calculation. So we lump these together and call them unmeasured cations, which I'm going to describe as UC. So you've got the sodium, you've got the potassium, and you've got all these unmeasured cations, and they have to equal these unmeasured anions in order for this particular rule to be accurate. And so the unmeasured anions that we have the anions that we do measure are chloride. Generally, that's the most common anion we have, and bicarbonate. Now we've got some unmeasured anions. Actually, we have quite a few. Let's just go through them real quick. We've, of course, got albumin. It carries a 3 negative charge. We've got our phosphates. We've got our sulfates. We've probably got some lactate. Maybe some keto acids. Various charges. So these are all lumped together and are the unmeasured anions. So what we're going to do now is try to figure out how we get the serum anion gap formula that you're accustomed to seeing in the books, and hopefully provide you with an easy way of remembering the serum anion gap. So let's clean this up. So we're going to describe the serum anion gap as SAG. That's what we're talking about today. And we know that all the cations have to equal all the anions. So let's just put in all of our variables. We've got sodium, plus we've got potassium, plus we've got all these unmeasured cations that we could measure but we'll lump together as unmeasured. And we have to equate that to all the anions. So it's chloride plus some bicarbonate. Oh, that's doesn't look too good. Let's try that again. We've got some bicarb, and we've got our unmeasured anions. So you're probably not accustomed to seeing potassium in the equation, and that's because we're talking about the serum anion gap and in the serum you have very little potassium. So in most formulas, the potassium is just canceled out. You don't see it in the equation. But if you want to be a purist, you could of course include the potassium in there. So this really boils down to sodium plus all these unmeasured cations equals chloride plus bicarb plus the unmeasured anions. So if we do a little bit of rearranging, look at sodium minus the quantity of chloride plus bicarb is going to equal unmeasured anions minus unmeasured cations. This is the formula that we're accustomed to using. And this is what we describe as a serum anion gap formula. So if we have a serum anion gap, we're going to do some examples. Let's say you've got you calculate your anion gap and it's less than 0, meaning it's a negative number, -5, -10, what have you. That means that you either have no unmeasured anions, and that's not possible because we know unmeasured anions are albumin and lactate and keto acids and phosphates and sulfates. Those are all normal products of metabolism, so we can't have those values be 0. The only other way we could get an anion gap less than 0 is if we have a lot of unmeasured cation. So for an anion gap of less than 0, you have a lot of unmeasured cations. And this is commonly seen in conditions such as lithium toxicity or multiple myeloma, where you have a lot of IgG and IgM, which are commonly positively charged. These are common reasons to have an anion gap that's negative. Now let's look at an anion gap that's positive. Let's try to bring the screen down a little bit more. Or anion gap that's greater than 0. Well, in that case, you must have either no unmeasured cations, and that of course is not possible either, because you've got some traditional unmeasured cations in here that don't go away, like your calcium and your magnesium. So you really don't have an unmeasured cation of 0. So the only way it can be positive is if you have a lot of unmeasured anions. Now, you normally do have a lot of unmeasured anions because the most common unmeasured anion is albumin, and there's a lot of it because it carries a 3 negative charge. So the traditional belief, or excuse me, rule is that an anion gap, a normal anion gap, is about 10 to 12, and that's all because of the normal amounts of albumin with that -3 charge. If you have an anion gap even above the normal 10 to 12 range, then we're talking about some pathologic conditions. You may also have multiple myeloma, but this time with IgA, which is commonly a negatively charged antibody. You may have a lot more lactate than is allowed. You may have some alcohols like methanol or ethanol, ethylene glycol. Those are all negatively charged. You may have keto acids, and of course we'll squeeze it in here, acute renal failure, because of a tremendous amount of sulfates and phosphates, more than what you normally would expect. So let's clear this. And so the way I remember the serum anion gap is that I calculate it this way. But once I get my value, my number, I always try to equate it to this equation. And I try to figure out which one of these parameters is up, and then go through my differential of what could make you have a lot of unmeasured anions or a lot of unmeasured cations. And that's the simple explanation for how the serum anion gap has come into play in modern nephrology. Thank you very much. I hope you found this tutorial educational and helpful.